So this is Math 331, Lecture 22. This is sadly our last day doing contour integration, but we will at least do a really good challenging one. And if you decide that you just can't bear the thought that this is the last day, there will at least be a class on this next year. And there's also a complex analysis class going on right now that you can just crash. Okay, so the integral we're going to do today is the Gaussian integral. And I've posted some notes from a friend of mine that gives maybe 8 or 9 distinct ways of calculating this integral. It's extremely important. So the general one is the integral from minus infinity to infinity, 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared dx. And this is the density of a normal with mean mu, variance sigma squared, and since it's a probability density, it integrates to 1. So rather than actually calculating this integral, let's look at an integral that's very similar to this, but it's a lot easier. Which parameter do I want to get rid of first? When you look at this, which is the first parameter you can just say, oh yeah, just ignore it. Set it to a specific value. Not sigma squared. There's, I think, a slightly easier one than sigma squared to go with first. Mu, right? All mu does is translate the x. So your first step should be to take just mu equals 0. And that's not going to really change anything. So if I can handle this integral, I can do the more general integral. The next one is to say, well, let's replace t as x over sigma. So then dt is dx over sigma, or dx over the square root of sigma squared. And if I do that, I can drop the sigma squareds. So this is just doing standard change of variables. You know, this is not the exciting calculus yet. This is just trying to get it to a simpler one. So we'll get to the point where this is the integral we need to do. And once we can solve this integral, we can solve all the others. This is actually worth taking a moment and going back to something you've probably seen but have not really appreciated. So how many of you have taken a stats class? How many of you have seen probability tables of the normal distribution, the area under the curve? So they only do this for the standard normal. And the reason is if I give you any other normal, you can standardize the variable. So if x is normal with mean mu and variance sigma, let's let z equal x minus mu over sigma, and that will be normal 0, 1. So if you understand the areas under the normal, the standard normal, you understand the areas under any normal. I will say something even though almost surely none of you have ever used it. Log tables. Have any of you ever used a log table? When I was in high school, they made sure we could use not only log tables, but trig tables. Okay? I really don't get to use this knowledge that often. How many of you have at least seen a log table? Okay. Benford's law of digit bias, the fact that a lot of data sets are more likely to start with a 1 over other numbers, was discovered by looking at log tables and seeing that the beginning of the book was more 1 than the end. That numbers were more likely to have small logs. So there's a lot of great mathematics behind this. But there's really only one log table they give you, or maybe 2 or maybe 3. They might give you base 10, that's pretty useful. They might give you base 2, and they might give you base e. They won't give you anything else. And the reason is the most forgotten of the 5 log laws. So we've used the log of a product as the sum of the logs. We've used the log of a quotient is the difference of the logs. The log of a power is the power times the log. That's 3. Sometimes they do the inverse as a separate log. The log of 1 over x is minus the log of x, but come on, it's really just a quotient 1. There's a 5th log law. Anybody know the 5th log law? Change of base. So the log of x base b is the log of x base c over the log of y base c. And what this tells you is that if you understand logarithms in one base, y equals b. If you understand logarithms in one base, you can get them in another base. I hope I'm writing this correctly. Here, the way you would prove this is let's let y equal The log of x base b means some number y. Let's see. So it's b to how many powers equal x. So if I call this y, I get b to the y equals x. Right? I'm raising b by the number of powers of b I need to get x. Okay. Well, let's do things instead of base b, base c. I can write b as c to the log base c of b. That's the number of powers of c I need to get b. So then if I raise both sides to the y, I should have this equality. So this should just be equal to x. And now if I take the log of both sides with respect to c, I'll get the log base c of x is y log base c of b, just the power rule, because that's an exponent. And then the log of c base c is 1. And now I get y, which is my original number, is the log of x base c over the log. So if you haven't seen a proof of this before, it's worth seeing the proof of the log laws. What this tells us is if we understand logarithms in one base, we understand it in all the bases. The reason I'm saying this is I know this is the 21st century. You probably don't look at tables like this anymore. You probably don't look at tables of integrals anymore. When I was in college, we actually had to have 2 tables of integrals. You had the big table of integrals for your dorm room, and you had the small portable table of integrals for when you're on the go. I am not joking. I can show you the portable table of integrals in my office. Okay? They even have a little short cheat sheet of the really important integrals that you got to have on you at all times. Okay? 21st century is a little bit different. But one of the troubles of using all these things is recognizing when is this something that's in the book? When is this something that's known? How do I convert? So a lot of what we're doing is just talking about how do you convert things. All right, enough motivation. So we've now understood this. Now sometimes when we're doing problems like this, there's other tweaks you could do. Do we really need the 1 over square root of 2 pi? No. We can divide by the square root of 2 pi. Not a big deal. And then the last thing is, sometimes they have the 2 down below, sometimes they don't. It's quite annoying that different books decide to evaluate it with and without the 2. Doesn't make a huge difference, because you can always say, let's let u equal x over square root of 2. du is going to be dx over square root of 2. So if I don't have the 2, if I do have the 2, doesn't make a big difference. Okay, so the integral we want, we're now ready for the one. So I want to make sure I do things the same way, because I thought this was the nicest presentation. I want the integral from minus infinity to infinity of e to the negative x squared dx. And our first thought is, well, probably f of z is e to the negative z squared. And then this has worked so well for us in the past, let's try this again. So if z equals x plus iy, then f of x plus iy is e to the negative x plus iy squared. It's e to the negative x squared minus y squared. And I'll have a plus 2ixy with the minus sign, so I'll have a e to the negative 2ixy. So if we think about what's going on, what can you tell me about the magnitude of this piece, the e to the negative 2ixy? What's the size of that piece? What's its absolute value? 1. So this has absolute value 1. Remember, this is cosine 2xy plus I sine 2xy. This has absolute value 1. What about this piece? The e to the negative x squared minus y squared. Do I want to go in the upper half plane? Well, let's see. If y is larger than x, I'm going to get e to the negative of a negative number, which is e to a huge positive number. That's going to blow up. Okay, we don't want to do this contour. What contour should we do? So here, in this area, very large. So we're not going to get a negligible contribution when we integrate this. Plus we even have the length of the arc. So we're in huge trouble. So we can't do this contour because when we're close to x equals 0, we have a huge magnitude. So what contour should we try? It's okay if it doesn't work, but what should we try? So we tried, here's the x-axis, which is what we want, and then we tried going up into the upper half plane. If that doesn't work, what could we try? Lower half, right? It's not going to work. It's going to fail miserably, but it's the natural thing to try, right? So what if we tried going below? If we do this instead, well, now when we look at this, let's see what would happen. We have e to the negative x squared minus y squared. Does it really matter if y is positive or negative? No, we're squaring it. We'll have this problem down here. So neither approach is going to work for this one, unfortunately. There's another reason why we should be suspicious of this working. The whole point of Cauchy's residue theorem is we basically want to take the integral we want, we complete it into a closed curve, and then say, the completion either doesn't matter or it's something we can do trivially, and then it's equal to the sum of the residues. Where does this function blow up? No. Where does this function blow up? Is e to the negative z squared, does this ever blow up? No. This function is well defined everywhere. This is a bad function to integrate. Actually, I can tell you what the integral is over this contour. What's the integral over the contour? By complex analysis, what is the integral of this function over this whole contour? 0. It's equal to the sum of the residues. There are no residues. Right? So unfortunately, if we try to integrate this function over this curve, we get nothing useful. So what we want to do is we want to look at a tweak of our function that will give us the e to the negative x squared. But we'll have some places where it blows up. And this is where things get challenging, is trying to figure out exactly what can we do that will do this. This is one of the reasons why I like this problem. First of all, it's important. It's the normalization factor for the Gaussian. Enough of you have taken statistics that I don't have to explain why we care about normalizing the Gaussian. This is not a cookbook problem. The proof you've seen before is unnatural. You take the integral and square it and convert it with polar coordinates? It's a nice trick. What this does is this is going to show us how to really use complex analysis. All right, so we all agree that this, sadly, is not going to work? All right, goodbye. So I'm going to make sure I get the numbers correctly. Let's choose a to be 1 plus I. And I think I want a square root of pi over 2. How did I know to choose 1 plus I square root of pi over 2? It's one of my favorite math techniques. And the hint is I'm holding a piece of paper. What is the method? Divine inspiration, right? By the method of divine inspiration, let's take a to be 1 plus I square root of pi over 2. What we could probably do instead is we could take a to be some kind of constant and then try to figure out which constant is going to make things nice. In the interests of time, I decided to be divinely inspired today. Well, let's look at some nice things about a. If we look at a squared, well, this is going to just become a pi halves. And what's 1 plus I squared? We'll get 1 squared minus I squared, which is 0, plus 2I. So we just get pi I. So another way of writing this is the square root of I pi. That's probably a bad pi. That's a better pi. Why do you think we might be doing things involving square roots and squares? So why do you think a square might be a good thing to be looking at for this problem? So do you see any squares in the integral we're trying to do? Yeah, we have a negative x squared. So because we have, can you close the door? Because we have a square, it seems natural to try a squared equals I pi. So what you just missed was the motivation as to why we're trying this. All the other natural things failed. So you can watch that later. So now we are trying a new contour. We're going to consider the function f of z is e to the negative z squared over 1 plus e to the minus az. And now we're going to look, oops, I think they want to call that g. And now we can look at g of z minus g of z plus a. That's what I want to do, yes. And after some algebra, this is e to the minus z squared. So if we just do the different algebra, if we see what's going to happen, if we replace z with z plus a, we're going to square things. We'll have things canceling with this. It seems reasonable that as we go through the algebra like this, everything is chosen carefully enough so that this is going to work out. So this is just algebra. I'm not going to bother going through the algebra right now, but we can see that as we're choosing things, things should hopefully work out nicely. Okay, why might this be useful? Well, the point here is that maybe we can use this to get a nice rectangle to integrate. And we can replace the top and the bottom. We are going to combine and give us e to the negative x squared. So before, in everything we were doing, we were just having the bottom integral of our closed curve was the integral we wanted. Now what we're having is the bottom and the top together combine to give us what we want. And we've now set it up so that this function could actually have some poles. Where is this function going to be 0? What do we need to happen for this function to be 0? So where do we get the poles? Yes?
The function 0? Or
I'm sorry, the denominator is 0. The denominator is 0, sorry.
e to the negative pi I. So az would be pi I.
So we would need az. So we need e to the minus az equals -1. So we need minus az to be in what set? So you said pi I is a possibility? Yeah. So is minus pi I. Or does that work?
Isn't minus
No,
pi
no.
the same as pi?
Right. But would minus pi I work? Or would I be off by a minus sign?
No, that would work.
What about 3 pi I? Would that work? So I could have pi I plus or minus maybe 2 pi n. 2 pi I n. Because every time I increase by 2 pi, I've got e to the negative 2 pi I n. Well, e to the negative 2 pi I n is just 1. So when I look at the places where this has poles, these are the poles. So this function has infinitely many poles. They all lie on the imaginary axis, getting higher and higher up. Okay? So now what we want to do is we want to set up a rectangle to do the integration. Okay, and so what I'm hoping is that I haven't made a small mistake with the algebra. So here's minus r, here's r. I want to go up a little bit. And this will be r plus I times the imaginary part of a. And this will be minus r plus I times the imaginary part of a. and here's 0. So there's my contour. I've got to choose which function I want to integrate over this contour. What about the poles? Well, the poles are going to be are going to depend on what we integrate. So let's try integrating this function g of z. So we'll integrate it over this closed contour, g of z dz. Which of these poles are going to lie inside?
Like the pi I plus 2 pi I.
Yeah, which ones of those are going to lie inside?
From pi I to whatever n would be, so that it's just like right onto the top.
So we've got to remember, this is minus az, right?
So it would be like the negative pole.
Well, so a is the square root of I over pi. So when we're trying to look at the size of things, if we take this and divide by this, pi divided by a, the absolute value of that is going to be of size square root of pi. And then it's not going to be purely imaginary. So it'll be a little bit below. So I believe the only one that's going to matter will be this one over here, that all the other ones will be outside. So only here at z equals pi I, negative pi I over a. Well, negative pi I, I'm sorry, a is equal to the square root of I pi, so I think this would be negative square root of pi I. And if it was pure imaginary, it would be hitting over here. Since we're getting a square root, we're going to be changing the angle, and it will come down over and through here. So it will be inside the region, and the next ones, I believe, will be too large. And I believe they'll all be outside. So we should be getting the residue of our function g at minus square root of pi I. Yes?
I have a quick question.
Yep.
Regarding the poles. Like, I understand how pi I would be a solution, but I don't really get how plus or minus 2 pi I n.
Okay, so if we look at e to the minus a pi I, sorry, we're replacing az with this whole thing. So e to the pi I plus 2 pi I n. This is e to the pi I, e to the 2 pi I n. So e to the I pi, if you think about your circle, e to the I pi is right over here. That's negative 1. And then this is cosine of 2 pi n plus I sine 2 pi n. Cosine of 2 pi n is 1. Sine of 2 pi n is 0. So all these pieces here are just 1.
Okay.
So what we're doing is we're just going around and around and around. Yep. So what I think I'll do is I'm going to just set up, yes?
Why would it be the residue of negative square root of pi I instead of positive square root of pi I? I know you solved for it there, but why would the negative square root of pi I be inside?
That's just the location of the pole. We had.
But why would the pole be in the region?
Oh, is that one not in the region?
Right, because the square root of I is at 45
Okay,
degrees.
square root of I is 45 degrees.
Like you could, both pi I and negative pi I
Okay.
values of az, so I think you could just get rid of the negative sign.
I think we should evaluate negative as z2.
Okay, so here, so let's double check then where the residue. Okay, so we've got, we definitely want this to be -1. Okay, so maybe it's the next one that we wanted.
So instead of setting negative az to be pi I, we want it to be negative pi.
We want it to be -pi. Okay, so that's the one that's inside. Okay, so the only one we care about is the one that's at pi I. Let me do this slowly or I'm going to make a mistake. So we have pi I, negative pi I, 3 pi I, negative 3 pi I, et cetera, right? Okay. And we want to find the value of z. So z is going to be these divided by. Okay, so let me just double check. So we have a squared was pi I, so a is the square root of I pi, okay? And now we want to be up above. So yes, it does seem like right. So, oh, I see. Well, I'm confusing myself. I'm looking at the set minus az. So what we really want is we want z to be in this set, where now we've divided by the minus sign. The minus sign can just be incorporated in right now, and then just divide by a. Like this. And so then the one that should matter is if we take z as pi I and take the square root, that would come down over here. If we took minus pi I and took the square root, that would come down over here. If we took, I think, 3 pi I and took the square root, it would be a little bit too high. So I think we want z equals pi I over a. Now, the notes I have over here says that the only residue, oh, they put a 2 in over here. All right, so that's why all of my numbers differ by a 2. All right, so there's a 2 over here which they need for the cross terms. So we would want a 2 over here. Okay, and then we just put a 2a down here. And so the only residue we care about is at z equals pi I over 2a, which is a over 2, because pi I is a squared. So they just wanted a 2 over here to make the algebra come out right, because when you square this thing, you're going to get a 2. Okay, so now we would know that the integral over this closed curve of g of z dz is the residue of the function g at the point a over 2. And when you just go through and you do the algebra, you get its minus I over 2 square roots of pi. Okay. So now we're left with the integral over the 4 pieces. So we have these 2 segments there, and then we have the other 2 pieces. So the hope is that we can use this relationship over here, g of z minus g of z plus a, to then basically just get an e to the minus x squared. And the minus over here is going to come from the fact that we're going along the top in the opposite direction. And so if you write a point down here as x, over here you can write it as x plus iy. And there, the y is going to be the imaginary part of a. Okay, so I'm not going to bother going through all that stuff. Let's just talk about the 2 vertical pieces. We need to show that we have decay on the vertical pieces. So I will then let you do the rest of the algebra at home. Let's look at the vertical pieces. So we have an e to the minus z squared over 1 plus e to the minus 2az. And we're on these vertical pieces, so x is either plus or minus r, and y goes from 0 to the imaginary part of a. So let's look at what happens. The e to the minus z squared, we get an e to the minus x squared minus y squared, e to the negative 2i xy. And then down below, we have 1 plus e. Now we have a minus 2az. Z is going to be x plus iy, so it's going to be minus 2a x plus iy. We have to be a little bit careful because a itself is 1 plus I times the square root of pi over 2. So I can replace a with 1 plus I square root of pi over 2.
What made you choose that instead of taking square root of pi?
Divine inspiration. The other thing is by doing it like this, I can actually expand this out and see what the real part is and what the imaginary part is, and work much easier. So for this part, in terms of why I want to place it like that, I can see what's going on a lot better. Let's look at what's going on up here. Y can't get that large. And x is of size r. X is huge. So the numerator is like an e to the negative r squared. We're integrating it over a very small part. As long as the denominator isn't close to 0, we're fine.
But there's a 1 on the denominator.
I'm sorry?
Never mind.
But we have x equals r. And so when you start multiplying out, when you look at the real part, you're going to get x times 1, and you're going to get a minus y. And so the real part of this quantity is going to be so small, the denominator is close to 1. So the denominator is close to 1. The numerator is close to e to the negative r squared. So the numerator is approximately e to the minus r squared. The denominator is approximately 1 in absolute value. So because of that, since we're only multiplying it by a length of size imaginary part of a, we're not integrating it over a very large region. The contribution from the two vertical pieces are negligible. Now all you have to do is go through and do the algebra that when I integrate it over this and over this, it all comes out and gets you, some copy of the integral of e to the minus x squared. So this is just algebra at this point. I'm not going to go through the algebra. What I want to do is I want to go through the complex analysis part. This is a non-trivial problem. You can do things a little bit differently by trying to put in some divine inspiration, or you can do things a little bit slower and put in some free parameters and try to figure out what you want to do. The difficulty was we needed something that blew up. And the original function e to the minus x squared, this is holomorphic everywhere. This is differentiable everywhere. It has no poles. We need to somehow tweak it with something that had a pole. And what we want to do is we want to tweak it in such a way that we get poles, and then the integral over the top is either identical to the integral over the bottom, or a constant multiple of it, or it combines Yes.
Well, it might still work anyways, but shouldn't, wouldn't you want like the slanted sides? Because A is complex, so when you add it, it'll give like, it won't just be the imaginary part.
For when we're combining things?
Yeah.
I think it works like this. It's possible. I mean, I would suggest just going through and writing down all the steps. You know, essentially, something like this should work. The book said that doing it like this works. My feeling is I can see enough of the cancellation here that something very close to this should work. The best way you find, if you understand technique, is to go through and put in all the details. And so I will admit I'm a little worried in terms of what goes on here, because we have A. Could there be a typo? Could this maybe be the imaginary part of A? Or something like that. So I wouldn't be surprised if there's a small typo. But the general idea is absolutely correct. That we want to take something and relate it to quantities that have poles. And that's the real challenge. Okay, there's a lot more we can do with complex. I really don't want to do more than this. I just want to show you how far you can push it and how it gets harder. And now what you do is you step back and you look at all the different integration techniques we have and compare this to the divine inspiration of the polar coordinates. I'm posting 8 other, I think, ways of calculating the Gaussian integral. You can go through them and you can decide which one do you want to vote for. Do like a family feud. We have 8 ways to integrate the Gaussian. Top 4 answers are on the board. And just see which people prefer. And start to see which way looks more natural to you than others. A lot of it is experience. The more experience you have doing something, the more natural it's going to seem. I've always wondered if the cartoon music, how many of you have ever watched Looney Tunes with all the classical music? Is this the best classical music? Or do we think it's really good classical music because that's the music we've grown up hearing when we've watched the cartoons? One of my physics textbooks in high school was talking about special relativity. And they said, these results may seem counterintuitive at first, but you have to remember most people don't have experience traveling at 3/4 the speed of light. It's a little bit amusing, but it's not a bad sentence. So now when you think back to what we did, where we shoved in this parameter e to the negative tx and differentiated, does something like that seem more natural? Are you able to get something in closed form? What's nice about the residue theorem is as long as we can calculate the residues, and we can do that with algebra, we can calculate these closed integrals. The problem is then we need to make sure that things are chosen in such a way that we get the integral we care about. Okay, so I want to end with a following exercise. Show there are only finitely many solutions in positive integers to 1 over x plus 1 over y plus 1 over z equals 1 over 2008. Where do you think this came from?
Some math competition.
Some math competition, yes. In 2008. Right? Do we think that 2008 really matters? No. Do we think that there's exactly 3 terms and we use x, y, and z? Do you think that matters? So how would you attack a problem like this?
I mean, as x, y, and z get really, really big,
Mm-hmm.
1 over x, 1 over y, 1 over z get really, really small.
Good.
So once x, y, and z are all greater than, 2008 times 3, their sum will never be as big as 1 over 2008.
Okay, so good. So if x, y, and z are all really large, we have a problem. There's no way they can add up to enough. Well, maybe what happens is z gets really large and x and y stay small. And you could have infinitely many solutions like that.
You could, but if z got really, really large, there's still like a certain number of differences between 1 over 2008 and 1 over z.
Okay.
And then you can do the same exact problem with 1 over x and 1 over y.
Okay. So what are you trying to do when you say you can do the same problem?
Well, it's 1 over
Right, so what you want to do is you want to look at simpler cases first. This is a general theme we've been doing throughout the class. If I give you a problem, ask, is there an easier problem that this is related to? What do you think the easier problem is that this starts from? Right? This is the problem we start with. Show that there are only finitely many solutions to 1 over x equals 1 over 2008. Not so bad. Right? So, again, when you see these general problems, ask, is there a simpler problem that we can build up from? Now that we know that, now let's go to 1 over x plus 1 over y equals 1 over 2008 and try to show that there's only finitely many solutions to that. Well, instead of showing that there's finitely many solutions to 1 over 2008, let's do things a little bit more generally. I should show that there's only finitely many solutions to 1 over n. The proof is very similar. And so now, let's show that there's only finitely many solutions here. When I have problems like this, I always like to introduce an order. Assume, say, x is less than or equal to y. It may not be necessary for the problem, but I really like to start by putting some kind of structure on x and y. And now we can use the argument you said before. Since x is the smaller, we can just keep increasing x. Given a value of x, how many y's could you have that work? At most 1. Right. So for each value of x, you have at most 1 y that works. Given x, at most 1 y works. How large can x get? Yeah. X has to be less than or equal to m over 2, or maybe m over 2 plus 1 just be safe. Probably m over 2 should be fine. Yeah, m over 2 would be fine. So for each choice of x, y is uniquely determined. So we now have this finitely many solutions. Therefore, at most, finitely many solutions. Do I need to say at most, or can I just say there are finitely many solutions? Okay, so why can I say there are finitely many solutions? I'm sorry? Yeah, so if there's no solution, does that count as there's finitely many solutions? I would be quite happy to say if there are no, but when you say there are finitely many solutions, it does seem to imply that there's a solution. At most 7 people will fail this class. Or finitely many people fail this class. Which statement do you want me to utter? Neither. But if I have to, if I say finitely many people, and again, this is the difference between mathematicians and human beings. When we say words, the words sometimes mean very different things. If I say there are finitely many solutions, does that imply that there's a solution? That's why I like to just put in the at most. I might have mentioned that years ago I was talking with the neighbor of one of my father's cousins who mentioned the first time the Red Sox gave him a World Series ring. And while you could have only 1 ring and use the word first, he had 3. All right, so now we know there's at most finitely many solutions to 1 over x plus 1 over y equals 1 over m. So now what we can consider is 1 over x plus 1 over y plus 1 over z equals 1 over, I can't use O, that's a bad letter. We'll use A. So that means 1 over z is 1 over a minus 1 over x minus 1 over y. Yes?
Sorry, I just had a quick question about the two fraction case.
Yes.
Would it be bounded to m over 2?
Well, because x is the smaller of the 2 numbers. We ordered them. So x is less than or equal to y.
I would think it's 2m though.
Oh, then it should be 2m. Okay, yes. Good call.
And then isn't it always true that there's at least one case that works, namely the case where 1 over 2m plus 1 over 2m equals 1 over n? Oh wait, no, but that doesn't mean x has to be smaller, right?
Well, no. I mean, if x and y equal 2m, then 1 over 2m plus 1 over 2. So now we can actually get rid of the at most, because now we actually have a solution.
Right.
So now we don't have to worry about the English. But now we see that there's a problem. What would we love to do here? You would love to say, or maybe we should do it the other way. Okay, here I'm having z less than equal to x less than equal to y. I want to play the same game as before. And say for each fixed value of z, there's at most finitely many solutions x and y. Why can't I do this?
Because if you were to like try and subtract the 1 over a, you wouldn't necessarily have a numerator of 1.
Yeah, we wouldn't necessarily have a numerator of 1. So we go all the way back here and go Pn over Qn. Finitely many solutions to that. We come over here. Do we really care that this is 1 over? So now we could try to erase this and maybe go Pm over Qm. But now do we have to worry that P could be large?
No, not necessarily, because if we do the same bounding technique right there,
Mm-hmm.
right? X would be less than or equal to 2q over p, or 2qm over pm,
Okay.
right? So all we have to make sure of is that you know, like even like if p is really large, that means that x is actually bounded more tightly, and in either case,
Right, because I mean, 1 over x plus 1 over y is still going to be very, very small.
yeah, and it's still going to be some real number.
It's still going to be some real number. And so in terms of being able to equal the Pm over Qm, in fact, we're going to have enormous trouble if Pm gets very large.
But can't we assume that PM is less than
Qm?
QM?
I think we can assume Pm is less than Qm. Because each term it's supposed to be adding up. So we only need to study this with, 1 less than equal to Pm less than equal to Qm. And so the same argument as before will show that there's only going to be finitely many pairs here that work. So when we want to try to apply it over here, we just have to be a little bit careful because this is not necessarily of the form 1 over an integer.
Why did we write it that way? Why can't we write it 1 over x plus 1 over y equals 1 over a minus 1 over z?
Oh, we could do it that way as well. So we can do it as, you want to do it 1 over x plus 1 over y equals 1 over a minus 1 over z. We can do it that way. And now,
For every z, there's a fixed amount of x and y's.
right.
And then there's a fixed amount of z's.
And we'll still have z be the smallest. So we'll still do z less than equal to y less than equal to x. So this would work as well, and this would give us one of these numbers. And then for each one of them, we'll have only finitely many pairs from above. Yeah. So we just have to be careful whenever you look at these problems. What is the base case? What is the earlier case that you want to expand from? And what might happen is that the natural case that you try, you might have to just tweak a little bit as you're going through the analysis. All right, so this is a good place to stop. So next week, we'll start getting to the point where you'll be doing presentations on the things you've looked at in the book or on your Project Euler problems that you like. And we'll start, I think, shifting to the last theme of the course, which is games and logic puzzles. And what can you tell me about all the games we're going to play?
They involve Kim and Kayla.
You could say they involve Kim and Kayla. Do you want to play me in a game that I suggest we play? No. These games are all rigged. They're all going to be rigged, right?